fabric of reality isn't quite what we think it is. What if space and time too aren't the fundamental bedrock? What if they actually emerge, pop into existence from something? Well, something even stranger, more deeply connected underneath. Today we're diving deep into one of the most profound and, let's be honest, speculative ideas floating around in theoretical physics. It's this conjecture that space-time itself, the stage for everything, is actually an emergent property, woven maybe from a universal network of quantum entanglement, and that this entanglement shows up geometrically as tiny microscopic wormholes. This is the ER EPR conjecture. Groundbreaking stuff.
It absolutely is. Frontier pushing, definitely. But it does build on some really solid, well, foundational pillars. You've got the Einstein-Rosen bridges, first ER bridges, those theoretical tunnels, you know. Then there's the Einstein-Podolsky-Rosen paradox, the EPR paradox. That really shone a light on the weirdness of quantum entanglement, its non-local nature. And then, yeah, the big one, the ER EPR conjecture itself, which basically says entanglement is a wormhole. They're the same thing. And if that's true, well, it's potentially a huge step towards unifying physics, getting gravity and quantum mechanics to finally talk to each other.
Okay, right. Let's unpack that. It sounds like we need to start where our usual picture of space-time, general relativity just breaks. It's singularities. So maybe walk us through that. What exactly are these pathologies of space-time? Why do they scream we need something more?
Yeah, good place to start. A singularity is essentially a point where everything goes haywire in general relativity. The curvature of space-time, density, temperature, they all mathematically shoot off to infinity. The equations just stop working, they crash. And it's crucial to understand it's not just some weird point in space-time. It's like space-time itself is sick. It's broken. It's a clear sign our theory is incomplete at these extremes. We need quantum gravity. And it's important to differentiate the types, too.
Ah, right. There's more than one kind.
Exactly. You've got the cosmological singularity, the Big Bang. That's thought of as the beginning of space-time itself. It was spacelike, happening everywhere at once, in a sense. But black hole singularities are different. They're local inside the universe. They're time-like or null in the future for anything falling in. It's like an endpoint within space-time. So the Big Bang singularity was the universe starting, you could say. Black hole singularities exist within the universe and their structure. Well, that's where it gets interesting for wormholes.
Okay, so it's these extreme points where geometry gets totally warped that we see the limits of classical physics. And you mentioned the structure of black hole singularities. Particularly rotating ones. How does that hint at a gateway or, a wormhole?
Precisely. For a simple, non-rotating black hole, a Schwarzschild black hole, you get a point singularity, a dead end, basically. But if the black hole is spinning, it has angular momentum. That's a Kerr black hole. And that rotation kind of smears the singularity out. It doesn't collapse to a point, but to a ring singularity. And theoretically, according to the math, this ring isn't necessarily an endpoint. It could act as a kind of gateway, a passage.
To another region of space-time, or even another universe.
Potentially, yes. That's the theoretical possibility. It's a form of Einstein-Rosen bridge. And that's where John Wheeler's wonderful analogy comes in.
The wormhole analogy.
Yeah.
Like a worm burrowing through an apple instead of crawling over the surface.
Exactly that, a shortcut through space-time. So these rotating singularities naturally pointed towards ER bridges.
But there was a huge catch with those early wormhole ideas, wasn't there? They were incredibly unstable.
Oh, absolutely. That was the killer problem. The original ER bridge models, based just on classical gravity, would collapse instantly. The throat of the wormhole would pinch off so fast, faster than light could even cross it. So completely non-traversable, useless as a shortcut. Which raises the question, how could you ever keep one open?
And that leads to exotic matter, right? This theoretical fix.
Exactly. To counteract that gravitational collapse, you'd need something with, well, anti-gravitational properties, something with a negative energy density or maybe a huge negative pressure, stuff that pushes space-time apart instead of pulling it together. That's what we call exotic matter.
Great. Exotic matter sounds exotic. But how real is it? Do we see anything like this out there? Or is it purely theoretical scaffolding?
Well, in classical physics, no known examples, nothing we've ever observed behaves like that. It violates what we call energy conditions, but quantum field theory throws us a bone, a potential loophole. Think about the vacuum, empty space. Quantum mechanics says it's not truly empty. It's fizzing with virtual particles, quantum fluctuations.
The quantum foam idea.
Sort of related, yes. And in certain configurations, like the Casimir effect, which has been experimentally verified, by the way, these quantum fluctuations can actually create regions where the energy density is lower than the surrounding vacuum, effectively negative energy density.
Okay. So quantum mechanics allows it? Kind of?
It allows it, yes, but with very strict rules. There are things called quantum inequalities. You can sort of borrow negative energy, but only locally for very short times, and you have to pay it back elsewhere. It's tightly constrained. So while it doesn't give us bulk exotic matter easily, it shows that negative energy density isn't completely forbidden by physics. It opens the door, especially for microscopic wormholes, possibly being stabilized by these quantum effects. And what's really fascinating is how this problem forces gravity and quantum mechanics right up against each other. You need one to solve the problems of the other.
Okay, that makes sense, like a quantum loophole for a gravitational problem.
Hmm.
So let's shift to that other pillar then. Quantum entanglement. We hear about it a lot. Particles linked, measure one, you instantly know the other no matter how far apart. Einstein's spooky action at a distance. How did he, Podolsky, and Rosen actually frame their paradox? What was the core issue for them?
Their core issue was really about locality and realism, this instantaneous connection. It seemed to them like information must be traveling faster than light, even if subtly, which would violate relativity, break causality. That was unacceptable. So they argued quantum mechanics must be incomplete. There had to be some underlying information, some hidden variables that the particles carried with them from the start, predetermining the measurement outcomes.
Like the gloves analogy. If you have a pair, one left, one right, put them in separate boxes and send them off. Opening one box and finding a left glove instantly tells you the other's right.
Right.
But no spooky connection needed. The information was always there.
Exactly. That was their preferred explanation. It preserves locality. The apparent connection is just because they started with correlated properties, no faster than light signaling.
But then along came John Stuart Bell. And he figured out a way to actually test this, right?
Yeah.
To distinguish between Einstein's hidden variables and the spooky quantum reality.
Yes, Bell's theorem was ingenious. He showed mathematically that if local hidden variables existed, the correlations between measurements on entangled particles would have a limit. They couldn't be correlated beyond a certain amount. Quantum mechanics, however, predicted correlations that exceeded this limit, this Bell inequality.
So it set up a direct experimental test. Measure the correlations. Do they obey Bell's limit or do they violate it?
Precisely. And the experiments, starting with Aspect in the 70s and repeated many times since with increasing precision, have overwhelmingly shown.
Quantum mechanics wins. Bell's inequality is violated.
Consistently violated, yes. The spooky action is real. Entanglement exhibits correlations stronger than any local classical theory can explain. It's fundamentally non-local. And this non-local connection, this verified spookiness, is the absolute key. Because ER EPR takes that connection and says, that's not just some abstract quantum link, that is geometry. That is a wormhole.
Wow. Okay, so the weirdness is real, proven real. But just to be clear, this still doesn't mean we can send messages faster than light using entanglement, right?
Crucially, no. That's a common misconception. While the correlation is instantaneous, you can't use it to transmit information faster than light. The outcome of any individual measurement on one particle is still random. It's only when you later compare the results from both sides using classical communication limited by light speed that you see the spooky correlation. Causality is safe.
Got it. Okay, so we have wormholes hinted at by singularities, potentially propped open by quantum effects maybe, and we have this proven non-local entanglement. Now we need to go really small to the Planck scale, where everything supposedly breaks down. What's that scale and what happens to space-time there?
The Planck scale is the basement level of reality, theoretically speaking. Planck length is about 1.6 times 10 to the minus 35 meters. Planck time, 5.4 times 10 to the minus 44 seconds. Utterly minuscule. Down there, our current theories, general relativity and quantum field theory, just don't work together properly. Space-time itself is expected to stop being smooth and continuous.
It becomes choppy. Quantum.
Exactly. It becomes a seething arena of violent quantum fluctuations, as Wheeler put it. This is his quantum foam concept. He imagined space-time at that scale being multiply connected, constantly bubbling with tiny virtual black holes blinking in and out of existence, and, crucially, microscopic wormholes forming and dissolving. Wheeler had this incredible intuition that space-time was too flimsy, too fragile at this scale. It couldn't be the fundamental thing. It had to be built from something deeper.
Something deeper. Like quantum information.
Entanglement.
That's the idea driving ER EPR. Space-time isn't fundamental, it's emergent. Think of it like the smooth surface of water emerging from the chaotic motion of countless H2O molecules. Here, the smooth geometry of space-time emerges from the connections, the entanglement of underlying quantum bits or degrees of freedom. Space-time is sewn together by entanglement.
Okay, so now state it plainly. What is the ER EPR conjecture? EA proposes a direct equivalence, a duality. Any two quantum systems that are in an EPR state, meaning they are entangled, are connected by an Einstein-Rosen bridge, a wormhole. It's not just saying they are like each other, it's saying they are the same thing viewed from different perspectives. The entanglement is the wormhole. The wormhole is the entanglement.
One is the quantum description, the other is the geometric description of the same underlying reality.
Precisely. And its origins, as you mentioned, came from studying black holes within the context of the ADCFT correspondence. That's a powerful tool from string theory that relates a theory of gravity in a specific type of space-time anti-de Sitter space, or ADS, to a quantum field theory living on the boundary of that space. Researchers found a specific case. An eternal wormhole connecting two black holes in ADS space was mathematically identical, dual, to a pair of maximally entangled quantum systems living on the boundaries. ER-EPR takes that very specific finding and says, maybe this isn't just about black holes in ADS space. Maybe this is a universal principle for all entanglement.
Wow, that's a huge leap. From a specific setup, too. Everything entangled is connected by a wormhole.
It's a very bold extrapolation, yes. That's why it's still a conjecture.
So the grand vision here is mind-bending. The entire geometry of space, the structure of time itself, is somehow encoded in or emerges from the entanglement pattern of all the quantum stuff in the universe. Like that quote you mentioned earlier, the solid structure of space-time is due to the ghostly features of entanglement.
That captures it beautifully. It suggests that the connections we see as geometry are fundamentally quantum information links.
And you said this has implications for resolving paradoxes, like the black hole firewall paradox. How does ER-EPR help there?
Right. The firewall paradox was a major headache. Briefly, it seemed like requirements from quantum mechanics, entanglement between Hawking radiation particles inside and outside the black hole, clashed violently with general relativity's requirement of a smooth, drama-free event horizon for someone falling in. It suggested a fiery firewall might exist at the horizon, which contradicts GR. ER-EPR offers a potential way out. It says the entanglement between the particle inside and the radiation outside is the connection through a wormhole bridging the black hole interior to the exterior radiation. So the spooky entanglement connection is the smooth geometric connection. There's no conflict because they are two descriptions of the same thing. The wormhole is the entanglement link. It dissolves the paradox by unifying the descriptions. It acts like a dictionary, translating between gravity speak and quantum speak.
Okay, that's elegant. It translates a quantum problem into a geometry problem, or vice versa, and potentially makes it solvable. But it still feels like a conceptual leap, doesn't it?
Oh, absolutely. The biggest leap is really internalizing this idea that geometry isn't fundamental, that the shape of space isn't just there. It's a consequence, a manifestation of these underlying quantum connections. We're used to thinking of particles moving through space, not space being made of the relationships between particles. That's the core shift in perspective.
Right. Okay, so if we accept this, even just hypothetically, and scale it up, if ER-EPR is universal, then the whole universe is this gigantic web of entanglement, right? Space-time is woven from zillions of these tiny wormhole connections.
That's the implication, yes.
And connecting back to the beginning, the Big Bang. Would that be seen as the ultimate source of all this entanglement?
Exactly. The Big Bang creates everything. In a hot, dense state, particles interact intensely. They become massively entangled on a cosmic scale right from the start. So the universe is born with this incredibly complex, universe-spanning web of entanglement, which, according to ERR, is the initial structure of space-time itself, woven from these microscopic wormholes. You can think of space-time less as a smooth sheet and more like a dynamic, evolving graph or network of quantum connections. Like a tensor network, which is a tool physicists use to model complex entanglement.
Okay, but wait. If wormholes are everywhere, connecting everything, doesn't that immediately bring up the scary stuff? Causality violations, time travel? Can I use my entanglement with a particle across the room to pop over there instantly?
Okay.
Or back in time?
That's the immediate and very valid concern. But the answer seems to be probably not. These ER-EPR wormholes are generally understood to be non-traversable. They reflect the correlations of entanglement, that spooky link, but you can't send actual signals or objects through them faster than light. Remember, you only see the correlation after comparing notes classically, so FTL communication seems forbidden.
So no sending messages back to warn myself not to eat that dodgy curry last night.
Unfortunately, no. And many physicists subscribe to something called the chronology protection conjecture. Basically, the idea that the laws of physics themselves have built-in mechanisms to prevent paradox-inducing time travel. Studies of ER EPR within consistent frameworks suggest macroscopic causality remains robustly protected. What's really fascinating, though, is that ER EPR might offer insights into why time flows forward at all the arrow of time.
How so?
Well, the universe is expanding, and generally, entropy a measure of disorder, but also related to entanglement increases. If space-time geometry is entanglement, then maybe the expansion of space and the increase in entanglement are linked. The stretching and growing of this cosmic wormhole network could be the expansion of space, and its increasing complexity could be the increase of entropy, giving time its direction. It's speculative, but deeply suggestive.
Linking the expansion of the universe to the growth of entanglement. Wow. Okay. But let's pump the brakes a little. This is all incredibly cool, very compelling,
Yeah.
but it is still a conjecture. You mentioned hurdles. What are the big theoretical problems, the inconsistencies people are trying to solve?
Yeah, there are some significant ones. A big one is reconciling the linearity of quantum mechanics with the nonlinearity of geometry. Quantum states can be superposed. An entangled state is often a superposition of unentangled states. If the entangled state is a wormhole, how do you get a definite geometric object like a wormhole from adding up states that correspond to no wormhole? That's tricky.
Like 1 + 1 with wormhole.
Sort of, yeah. How does superposition work on the geometry side? Then there's the issue with Bell's inequality again, but from the other side. Entanglement violates classical correlation limits, Bell bounds. But a classical wormhole, viewed just as geometry, feels like it should obey classical limits. How can one side violate them and the other not if they're the same thing? That mismatch needs explaining.
Okay, that sounds fundamental. What else?
A huge practical issue is the ADS versus DS problem. As I mentioned, ER EPR and the ADI-CFT correspondence work beautifully in anti-de Sitter space, this theoretical negatively curved spacetime. But our actual universe appears to be de Sitter space, positively curved, accelerating expansion. Making ER EPR work quantitatively in DS space is a major, major challenge. The dictionary might not translate properly. And another question, what happens to the wormhole if you break the entanglement? So you measure one of the particles. Does the wormhole just vanish instantly? How does that work geometrically? Lots of open questions.
Right. Theoretical hurdles aplenty. What about actually proving it? Is there any experimental evidence, any observations pointing towards ER EPR being true in the real world?
Okay, bottom line. Currently, there is zero direct experimental or observational evidence for ER EPR, or for macroscopic traversable wormholes for that matter. People have looked. Searches for strange gravitational lensing effects or specific signatures in gravitational waves from merging black holes that might hint at wormhole structures, nothing definitive has shown up.
So it remains purely theoretical for now.
In terms of direct detection, yes. However, there's been really exciting progress in the lab using quantum computers. Physicists have managed to simulate the dynamics of systems that are mathematically equivalent to wormholes, according to the ER EPR dictionary. They can create entangled quantum states on a chip and watch them evolve in ways that mirror information passing through a simulated wormhole. Now, to be clear, this isn't creating a real wormhole in space-time, it's a simulation. But it's a powerful proof of principle. It shows that the ER EPR translation between quantum information and geometry is mathematically consistent and can be realized, at least in these controlled toy model systems. It validates the dictionary itself.
Okay, so simulation, not reality yet, but it shows the math hangs together. So bringing it all together, where does ER EPR fit in the grand quest for quantum gravity, for a theory of everything? Is it the leading idea or just one competing approach?
It fits most naturally within the framework of string theory because, as we said, it grew out of the ADI-CFT correspondence, which is one of string theory's major achievements. Within that context, it's seen as a potentially crucial insight into how spacetime emerges and how gravity and quantum mechanics unite. It offers a different perspective compared to, say, loop quantum gravity, LQG. LQG starts by quantizing space-time itself, imagining discrete atoms of space and time. It typically deals with singularities differently too, often predicting a quantum bounce instead of a singularity. Interestingly though, even in LQG, researchers have recently started exploring wormhole solutions and entanglement more. So while they start from different places, there might be hints of convergence down the road. It's not necessarily strictly one camp versus the other anymore.
Fascinating. Okay, so let's try to summarize this deep dive. The core idea, the really mind-blowing takeaway, is that space-time, the stage of reality, might not be fundamental at all. Instead, it could be an emergent property, a dynamic structure literally woven from the ghostly threads of quantum entanglement, a synthesis of Einstein's geometry and quantum weirdness.
That's it exactly. It's an incredibly powerful idea because it offers potential solutions to deep puzzles, especially around black holes, and gives us a radically new way to think about the relationship between geometry and information, between gravity and quantum mechanics. But yes, we have to keep emphasizing it's still on the speculative frontier. It faces serious theoretical challenges, and as yet, there's no direct experimental proof. It's a beautiful, compelling picture, but the jury is still very much out.
And the path forward seems clear, if challenging. More theoretical work, refining the idea, trying to solve those inconsistencies, applying it properly to our kind of universe, the de Sitter one. And on the other side, pushing experiments and observations, looking for those subtle gravitational signatures with better telescopes and detectors, exploring black hole physics, and continuing those fascinating quantum simulations.
Precisely. It's a parallel track of theoretical development and experimental probing. The quest to figure out if ER EPR is right, if spacetime truly is woven from entanglement, is really inseparable from the entire quest for quantum gravity. It's a journey right to the foundations of what space and time are. And maybe a final thought for you to ponder. If this is true, if entanglement is geometry, what does that mean about connection? What if every interaction, every shared quantum state, every bit of entanglement created between particles, including those in you and me and everything around us, is literally in some deep microscopic way knitting us all into the very fabric of the cosmos itself? What if connection is the structure of reality?